Good afternoon, all. It's good to see you. I see some friendly faces online and some new folks here. Welcome to our veggie irrigation efficiency workshop webinar, throwing all the words at you. We have an amazing presentation today led by Chad Cochrane from the New Hampshire NRCS. This is a part of a larger series of energy efficiency webinars and workshops aimed to empower producers to discover options for their farms, find resources to get some of this amazing work done. There's an unprecedented amount of federal money flowing to this kind of work, and a lot of collaboratives taking place. And so it felt like the right time to be linking growers to the options available to them. My name is Matt Smetana. I'm the Community Engagement Coordinator for the Cheshire County Conservation District. Cheshire County is the southwesternmost county in New Hampshire. We're nestled next to Vermont and Massachusetts in hills and forests, lots of water around here. And our agricultural operations are a bit smaller than you might see out in the Midwest, with some nuanced considerations. Today's presentation is going to focus on agricultural operations in the Northeast and irrigation options around these parts. If you are not from the Northeast, you might still find some value in what's being talked about today. So we encourage you to stick around. Like I mentioned before, this workshop is a partnership between a few different organizations, one of which is the Cheshire County Conservation District. Conservation districts are located in every county in the United States. We provide education, financial resources, a lot of opportunities for communities, a lot of which center around agriculture. So if you haven't engaged with your conservation district before, we encourage you to take a look, do some Googling, see who your county conservation district is and what they can do to support you. Some of the other partners on this webinar today are the New Hampshire NRCS, which we'll be learning a little bit more about in the near future, and NOFA New Hampshire, our Northeastern Organic Farmers Association. And we have a representative from NOFA New Hampshire today to mention briefly one of their amazing programs. Teresa?
Thank you, Matt. I'm Teresa Downey. I'm from the Northeast Organic Farming Association of New Hampshire, one of 7 chapters throughout the Northeast. I'm also the TOP coordinator, and that TOP stands for the Transition to Organic Partnership Program. It is a USDA funded program for 5 years, and $100 million has been put to this program. It's broken up into 6 regions in the United States, and it is a mentorship program as well as technical assistance. So farmers who are interested in transitioning to organic, or organic farmers who are currently certified and want to expand their scopes or their acreage can qualify for this program. It is a free program for any farmer who is interested in transitioning. You can find out some more information. I'm going to put some things in the link. And you can reach out to us at NOFA, New Hampshire, or you can go directly to the national website, and then it kind of gets funneled back to us. Takes a couple weeks sometimes for that to happen. But it's a mentorship program, and I noticed we have at least one mentor that's currently in the program on today. So if there's questions, maybe they will be interested in answering some of that. But I'm also happy to answer any questions you might have later in the program. Thanks so much.
Thanks, Teresa. And like Teresa said, we'll be putting some stuff in the chat throughout the presentation. I'd like to go through some ground rules for today. We'll be hearing our main presentation from 12:30 to 1:30. And if there's any questions, we encourage you to post them here in the chat. In the meantime, I'll be moderating while Chad is presenting, and we'll cover those at the end of the presentation. We might have some time after 1:30 to cover those questions if you wanted to stick around a little longer, but we're officially ending at 1:30 today. We ask that you please stay on mute during the presentation so we can hear Chad. Sometimes background noise can get a little challenging for some folks to hear. We'll be posting some resources as we go, so you'll see some links pop in the chat, and we'll be providing a follow-up email after today's webinar, including a recording from today, which you probably got a little notification about, and some of those resources that you'll be seeing streaming through the chat. Feel free to reach out to us throughout the presentation if you have any questions. And I'll be turning it over to Chad in just a second. So Chad Cochrane, he is our state agronomist here in New Hampshire for the USDA-Natural Resources Conservation Service. He works statewide promoting conservation agronomy, sustainable agricultural practices, and soil health management systems. Chad's been a lead supporter and promoter of no-till planting methods, use of cover crops, and irrigation water management on all sizes and types of farms. He's a fantastic educator and a good person, and we are very lucky to have him today. Chad, want to take it away?
Yeah, sounds great, Matt. Thank you so much. Excited to be here with all of you to talk about this. I'm going to share my screen. Get going here. All right. You guys seeing that?
Yes, we are.
Perfect. All right. Nothing like getting going and not having your screen share work. Yeah, so like Matt said, I am the state agronomist here for the state of New Hampshire. And just to point that out, I guess, that the focus of my talk today is going to be New Hampshire specific, New England, Northeast specific. So if you're joining us from outside that area, some of it's going to apply. Some of it might be a little bit more of a regional flavor than where you're at. But hopefully we have mostly a local audience on today, and excited to maybe get some questions at the end and see where everyone's at with irrigation, specific questions and that type of thing. I'm going to cover things here in this next 45, 50 minutes at a fairly high level. So there's a lot more in the weeds details we could talk about if we wanted to. But the focus for today is going to be specifically on irrigation system efficiency, not so much on design and that type of thing, which would also typically be covered by our engineering staff here within the NRCS. I'm going to talk more about the management of your irrigation systems and how to make that management more efficient. I want to talk about, though, kind of the various types of irrigation systems that we typically see up here in New Hampshire and the Northeast. Talk a bit about plants and soil water and some of those concepts, because that's really important as you understand how irrigation systems influence both plants and soil water, and then how you can use those principles to understand monitoring soil water so that you are irrigating enough but not too much. And then last but not least is some funding opportunities through our agency, and I then know Matt has some other opportunities through grants in the conservation districts, so leave some time open for that at the end as well. First thing first, though, I do want to boldly put my disclaimer up there that when we're talking about irrigation systems, it tends to be very product vendor specific. It's one of those types of conservation we do that is tightly tied to specific products because that's what irrigation systems are. They are commercial products in the marketplace. So I'm going to show some of those through pictures and things during my presentation, purely for demonstration purposes, not an endorsement of any type. If you see a picture of one thing, there's probably another vendor that makes a similar type of product. So just know that it's purely for educational and demonstration purposes. So to start, it's good to talk about what we mean by efficiency of an irrigation system. And it really starts all the way from how we're storing water to the way we're moving water around the farm through conveyances. and then how we're then getting that water actually to the plant, the application of the water. And what we're trying to do that entire time is reduce loss. And it's really kind of baked into two different types of losses. One being energy. Can we move the water around by using less energy? And then can we apply that water through water use efficiency in a way that maximizes plant availability? So we're not losing it to, let's say, the atmosphere runoff or depercolation through the soil. So we're going to talk about it from those two specific efficiencies. First off, we're going to talk about, though, basics of a design of the way a irrigation system gets kind of built from all the pieces, you might say. This is very, very high cut, just so you know where I'm coming from, and we're all kind of having the same foundational knowledge as we're discussing the rest of the presentation here. But irrigation systems start with a water source of some type. It could be like the photo here, drawing from a pond or a stream. It could be a shallow well, could be a deep well, could be municipal water for an urban garden, right? There has to be some sort of water source, and that water source is going to dictate a lot of the rest of the design features of your irrigation system. The first being how we're going to move that water from the source to the crop field. You need some sort of pump. It could be a gasoline powered pump like we're seeing here that's going to suck water out of a pond and push it toward a field, or it could be a pump that is down in the water source itself like a well. Doesn't necessarily matter, but there's almost always some kind of pump involved in irrigation systems. There are few and far between, but there are some gravity fed as well, but pumps are the norm. And then you have to move the water around, and you're going to do that with a series of pipelines. Often you've got to filter the water, especially with micro or drip irrigation systems. You might want to add fertilizer to your irrigation water that's going out into the crop fields. And in some systems, you've got to be able to regulate the pressure because they operate at low pressures instead of high pressures. And last but not least, the part that we think about the most is actually applying the water to the field. But it's really only the last step in a whole train of things. And there are opportunities for efficiencies through that entire system, especially on the energy side. The first being our pumping plants, right? The type and size of pump that we're using. And the big thing here is that, no surprise to anyone, there are lots of different pumps out there, and they must be sized to the task. So what is the amount of water and how quick do we need it to a given field? And if a pump is not correctly sized to the task, it's not going to operate efficiently. And we look at that by looking at pump curves. And I'm not going to get into this in any detailed level today. We just don't have the time for it. But this is what an engineer or a designer would look at when they are trying to figure out whether or not a pump is operating efficiently. So every pump is going to have a pump curve, and it basically compares the amount of flow we need out to the field and comparing that to the amount of kind of pressure or work required to get the water there. And that is displayed in total dynamic head, measured in feet, interestingly enough. Not going to get into that a whole lot, but just to say it's kind of flow versus the work of moving water. And pumps are going to have a range in which they operate most efficiently. So this particular pump, let's say we wanted to be able to move 4 gallons of water per minute out to our, let's say, a high tunnel irrigation system. And the amount of kind of work we're up against to get the water there is about 25 feet of head. That, what you do is you just draw lines up through these graphs to where they meet, and then you can see those those pump efficiency lines that run through there. And you can see that we are within the most efficient range of the pump right now. This pump operates at about 70% efficiency in this scenario. And you can see, though, if we have less or more water needed, or that amount of work, that the dynamic head goes up or down, we're going to move around in the efficiency range of the pump. So that's what I mean by matching the pump to the task. And this is something that you won't do likely as a landowner or a farmer. You're going to get input from, a well manufacturer or a vendor or an engineer in this process. But it's just something to know that we do need to try to make sure our pumping plants are operating in an efficient zone. And it's also good to remember that this is the efficiency of the pump itself, not the engine or motor running it. It's really that the pump portion that is moving the water. And then there's another set of efficiencies for the motor and the engine itself. Not going to get into that at all today. The other thing with energy efficiency is pipe sizing. That if pipe diameters for our system are too small, it creates restrictions within the system that make the pump have to work harder. So that total dynamic head, that feet of head, starts to go up because we have to work harder to move water through a smaller diameter pipe. So sometimes it's as simple as making sure that our pipes are sized correctly to the amount of flow that we need. And if our pipes are too small, it doesn't just create more work, it can also force water through the system at higher pressure and higher velocity, which has some other implications as well for the longevity of the irrigation system. Obviously, higher pressures and velocities wear more and can create other issues within the system. So that's largely energy efficiency that I'm going to talk about today. And this is very much an engineering design related process that probably deserves many, many more hours of discussion than we have. But just wanted to put that on everyone's plate and on everyone's mind. And I want to talk basically for the rest of the discussion today about water use efficiency, which is reducing losses from evaporation, runoff, and deep percolation within the system. And the biggest one that most of us, we can see and really kind of wrap our heads around pretty easily is evaporative losses, right? It's when we are shooting water through the air in an irrigation system, and we have just that water going into the air as water vapor. But we can also have evaporation from the soil, from wet soils. And then whenever a plant has intercepted some of that water and the plant's now covered with water, that water is likely going to just evaporate. It's not going to go into the soil and be plant available. So we've got a number of places where we have evaporative losses in the system. Largely that's determined by the irrigation system, but also a little bit about the time of day. And by that, I mean that if we are shooting water through the air, like I mentioned, like this traveling gun here, if you're doing this during the hottest time of the day, the middle of the day, you're going to have more evaporative losses than if you did it at other times of the day. There may not be an opportunity to do it at another time. You might have to run your irrigation system 12 hours a day just to keep up with water needs, like during a drought. You don't have an option, but that's where, if you have a more efficient system from the start, you're going to be better off. So this is a traveling gun, or a big gun, they're sometimes called. And as you can see, they move a lot of water very far and very fast. That is both a blessing and a curse of these systems. So you can cover large acres with a lot of water quickly with a traveling gun. They operate at very high pressures. They also put the most amount of water out in a certain amount of time, but that kind of comes at some costs as well. These are the lowest efficiency systems that we see up here in the Northeast. The only thing that would be worse would be like flood or furrow irrigation, which we just don't see at all. So, realistically, these are 60, 65% efficient in a lot of cases. There's large variation from system to system, operator to operator in exact efficiency numbers, but kind of just knowing these are the lowest because we're shooting water the furthest. And because of that too, there's the greater potential for the water to overwhelm the soil's ability to infiltrate. So literally to soak in, like a big thunderstorm, too much water too quickly we have the potential for runoff and erosion along with the runoff. So that's kind of an added concern with traveling guns. This is probably what we all think about with kind of a classic irrigation system, our impact sprinklers. The kind of next on the list from going from least efficient to most efficient here. And they are kind of operating in a medium to high pressure scenario as well. They're put in on a grid known as solid set. So they are a relatively rigid grid that doesn't really move around. It's not very flexible, generally speaking. And they put out a high volume of water. They're not terribly efficient. They're certainly better than traveling guns, but they do also have potential to overwhelm the soil and cause some runoff and erosion if not operated carefully. So a lot of the effort is moving away from impact sprinklers with commercial irrigation toward more modern type of sprinkler systems like these. A number of manufacturers make these style or similar style irrigation heads now. These particular ones, they shoot water in two directions at once, so they're balanced and they rotate very smoothly versus that click, 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 click of an impact sprinkler. One thing that's very good about them is they water very uniformly. So whether we're talking close to the sprinkler or far away from the sprinkler, water is being uniformly spread, which means you don't have dry areas of the field and wet areas of the field. You're not underwatering one spot and overwatering in another. And that in itself is an efficiency gain. These are more efficient than impact sprinklers. They move less water, so they are gentler on the soil. They have less impact on soil aggregate structure. They maintain infiltration better. And this is really where a lot of people are now going, where they need to have overhead irrigation. Good example of the need for overhead irrigation is frost protection. This photo is a strawberry patch. Common application there is to coat strawberries with ice during a freeze to prevent them from getting essentially frostbite and ruining the fruit. So that's a great use of this type of sprinkler. But this is what we're all looking to go toward when we're talking about efficiency, is toward micro irrigation systems, where we are, instead of spraying the entire field with water, we're watering the individual crop row. Or in some cases, individual plants. So we're not watering where the plants aren't, which is just flat out a gain in irrigation efficiency. These operate at lower pressures, which means a lot of times pumps can be smaller. We gain some energy efficiency there as well. The volume of water tends to be lower as well. They're very high efficiency. We're often talking 90+% efficient, meaning that of the water that we are putting out onto the field, 90 to 95% of it is actually being taken up by the plant. That's what we're meaning there. So we have a far lower loss. Near perfect uniformity if these systems are designed properly. I guess the one big downside specifically with irrigation tape that I hear quite a bit, which I understand as well, is that it's not reusable. It's a disposable product. For a lot of people, that just rubs them the wrong way, understandably so. Good to know there are some tapes that can be used for multiple seasons, heavier duty tapes, and then there's also drip tubing, which is a far more expensive product, but it's a completely reusable, long-lived product that can be used as well. So there are some other options out there. They tend to be cost prohibitive on larger scale, but they are there. And I just want to pause for a second to just remind everyone, when we're talking about irrigation efficiency, is that the plant water needs are always going to be the same, regardless of the type of irrigation system you have. And sometimes that gets people a little bit confused. They think that they're going to save water because they're going to drip. That may be true, But that's only if they were overwatering before. If you were underwatering before with your inefficient system, you may find out you actually need to irrigate more simply because you weren't meeting the plant need in the first place. So it all depends on where you're at. The plant water needs are the same regardless of the system type. And we save water by having fewer losses. Seems really obvious, but I've seen many people get kind of crossways on this concept when they're trying to kind of wrap their heads around what efficiency means. But there's some good considerations to keep in mind when we're thinking about plants specifically. What is the weather we're having or going to be having, right? Because the hotter it gets, the more plants evapotranspirate water. They're going to suck more water out of the soil. We all know this, but it's good to keep in mind as we're thinking about managing the system. Another thing is how mature are the crops that we have in the ground right now? Are they young, shallow-rooted with lower water needs, or are they mature? Are they setting fruit? Are they blossoming? How deep are those roots and what are their water needs? And then also, what are my soils? And that's really what we're going to talk about next. And we're going to talk about that from the perspective of the concern about deep percolation. And this is where we are irrigating really too much or too fast, and we are having water move down through the soil beyond the root zone of the crop, meaning beyond where we can have any of the crop utilize the water. And that is in itself also another efficiency problem, right? We've applied water, but the plant isn't using it because it's too deep. And I want to have a little bit of time to talk about the way soils work with regard to water. And if you think about soil as a sponge, I think that's a helpful analogy. Some people think of it as a reservoir, but soil is made up of particles that have a lot of pore spaces in between those particles. And between those pore spaces, you can hold water. And the amount of water a soil can hold varies. Varies on the texture. Is it sandier? Is it siltier? Does it have clay? It varies based on its soil health, the amount of soil organic matter we have. All of these things play a role. And it's called the available water capacity of the soil. And it is between conceptually 2 points. One being the wilting point of the soil. That's when the soil is very dry. And although the soil may feel wet, plants are not able to suck that water up into their roots. It is being held in on the soil particles themselves too tightly, and plants can't get it. On the other end, on the wet end, we have a concept called field capacity. And that's when soils are holding their most amount of water that they can, while still maintaining enough space for oxygen. So we're not in a saturated condition. It's typically maybe a day or two after soils have been saturated, like a heavy rain. So it's like a theoretical maximum amount of water that we can have in the soil. And that's our available water capacity. And that's an important thing to keep in mind. We have on the left here, saturated soils where we have all of those pore spaces filled with water, no air. Moving to the right, we have field capacity where we have a lot of water in our soil, but from a plant's perspective, this is ideal because we still have plenty of oxygen too. And then on the far right, we have the wilting point, permanent wilting point, which is kind of the danger zone, or maybe past the danger zone for irrigation. This is where plants can no longer extract water from the soil, and they are going to be permanently impacted by that. In saturated soils, water it's no longer held in the soil. It's actually pushed downward in the soil profile by gravity until we get to this field capacity situation. When a soil's at field capacity, gravity's no longer acting on that water. The water's being held in films on the soil particle itself. Kind of a cool concept. And then that water is being sucked out generally by plants or just by evaporation of the soil. But what I want to do now is flip the soil up vertically like a profile, like we were looking at a hole in the ground. And if you think about the way irrigation works, we're adding water almost always to the top of the soil. And we're using gravity to move it down through that soil profile, right? So we're going to saturate the upper layer, and gravitational water is going to move that water down through the profile as we apply more and more water to the top, right? And then when we think about our plants, they have roots that go to a certain depth. They don't go forever, they go to a certain depth. And what we want to try to do when we're irrigating is add enough water to reach field capacity from the top of the soil surface down to the maximum rooting depth while minimizing losses below the roots to deep percolation. And the question is, I can't see down there. How on earth am I going to know how much water I have 6, 8, 12, 18 inches below the soil surface? And that's where we're going to start to talk about soil moisture sensors. Because we need to be able to monitor our soil moisture if we're ever going to wrap our heads around this whole deep percolation problem. On the flip side, though, it can also tell us when we're not irrigating enough and we're actually starving our plants from water and potential productivity, and we don't even know it. They haven't reached a wilting point yet, but they're also not in an ideal condition. And if we have adequate water, we can do that. If we don't have adequate water in our source, then we're going to probably manage somewhere in between there. But soil moisture sensors are a tool for evaluating how much moisture you have in your soil. No surprise there, given the name. There are two different types of sensors, though, that I want to talk about because this gets a little bit confusing. And when you Google soil moisture sensors, you're going to see both of these types. And they operate, and the way that you use the data is very, very different. Typically, with field irrigation on a vegetable field, like we're talking about today, or a fruit operation for the same matter, we're really going to be looking toward these water potential sensors, which indicate not just the water in the soil, but how much of that water is going to be plant available. Because we talked about how water sometimes gets held in soil films and isn't plant available. Where volumetric sensors, the one above there, they tell you just the total volume or amount of water in the soil, period. They're very accurate at doing that. They read very quickly, so they can read changes in soil water very quickly, but they really don't give you an indicator of how much of that water is available to your crop. So that's a problem, no doubt. These are what volumetric sensors look like. Again, these are the ones I'm kind of gently steering people away from. They're good at what they do. They read the volume of water accurately and quickly. They're very commonly used in greenhouses where you have a very even controlled growing medium. If you're growing in a greenhouse, if you're growing in pots or something like that, this is probably the right tool, actually, in that situation. But out in a crop field, they can become hard to calibrate and know how much of that water is available to plants. So what we use instead, generally speaking, are these water potential sensors instead, like I described. And they're essentially mimicking the way a plant root would be able to extract water from the soil. You'll notice they don't have probes. Just go back one here. The volumetric sensors have typically these probes, and they're going to send an electrical signal between the two probes and read the resistance between that signal, because we know electricity travels through water. The more water you have, the easier the electricity travels. So kind of pretty simple in that way. These water potential sensors are different. You're going to have water soaking into the sensor, mimicking kind of plant availability, or being pulled into the sensor with that, that tensiometer on the far left there. And that's going to, again, give us a better indicator of how well is that water actually available to the plant. Is it able to soak in, or is it not able to soak in? Not just whether it's there or not. Several manufacturers make these, and I'm just going to kind of flat out put a big red X over the tensiometers there on the left. They have their place. They're certainly still accurate and usable. The problem with them is that they can't remain in the field over winter. And I've seen a lot of these become ruined when they're left out in crop fields during freezing conditions. So not necessarily anything wrong with them. They're more labor intensive. They have that propensity to break in cold weather. So I'm gonna, for at least this presentation, steer people toward the regular ones to the right there that are electronic as well. And when we're dealing with soil water potential, we're dealing with measurements in centibars or kilopascals, and they essentially mean the same thing for our discussion here today. They're essentially synonymous. What's interesting about it, though, and I like this dial gauge here in this graphic. I'm a visual person, so I like the analog nature of it. If you look there, down at 0, that is saturation. So the lower the number, the wetter the soil. And it kind of goes back to those original tensiometers that I was mentioning. That's why this is the way it is. But it kind of, you have to flip your thinking a bit as you're working with these. So low number, wet, high number, dry. And what you're going to do as a manager of an irrigation system is set a point where you are going to allow the soil to dry to a certain degree. You're going to obviously wet it with irrigation and then allow it to dry to a certain set point. And that allowance is, we call that our MAD level, or management allowable depletion. It's not something you have to know, but it's something you might see in some irrigation literature or if you're searching on the internet. So just know that's essentially how dry are you going to let things get? What's your tolerance for dryness? That it's going to be crop related, going to be soil related. To some degree, it might be you related as a manager, but it's also, the drier things get, the riskier things get. The drier things get, the more water it's going to take to fill up that soil reservoir. So you're going to have to run your irrigation system longer to replenish soil water, versus if you let things dry out less, you got to irrigate more often, but you're going to irrigate a lower volume of water. Hopefully that makes some sense. So you as a manager, you're going to decide, like, okay, where am I going to start irrigating on this centibar, scale? A lot of times in New Hampshire, with our type of soils we have, which are a bit on the coarse side, the sandier side, we're about 30 or 40 centibars. That's a pretty good number for a lot of our crops, a lot of our soils. And then we're going to stop irrigating, once we get to around 10. A lot of times, though, we're going to have to irrigate all the way into that saturated zone, though, because remember, saturated water is what is going to push water down through our soil profile. That's that gravitational water. So, during the irrigation process, we're going to have saturated conditions. But when we're done, we want to get back up into that field capacity range within about a day or so. So I want to look back at this, knowing what we now know about soil moisture sensors and monitoring soil water, and think this through again, because we want to have a soil sensor down here at our deepest depth, the deepest depth that our plants are going to grow roots down to. For a lot of our crops, it's going to be in the 12 to 18 inch range. It's going to vary a bit. I'll talk about that next. But down here, deep in the soil, we've got fewer roots. So it's going to be, and we've also potentially got some subsurface water. We might have water down that deep coming up, wicking up through our soil through capillary action as well. So things tend to be more stable at our lower depths. They tend to change more slowly. And we also want to have a shallow sensor as well, kind of midway between our soil surface and our deep sensor, sometimes maybe even a little shallower than that. And that's because in the top 6 to 8 inches of soil or so, plants have the most amount of roots, and they actually take up the most amount of water in that area. So that's a flashier part of the soil. It gets more solar radiation, evaporation is faster. So you can find that shallow sensor is going to see rapid changes in moisture where your deep sensor may not. And if you're always irrigating down to your deep sensor, you're probably over irrigating every time, okay? Where you place those sensors, I do want to mention, it needs to be on the actual crop rooting depth. Make sure you know your soils. Do you have compaction? Do you have rocks? What type of varieties are you growing? Looking up tables online, you can find that crops can grow very, very deep. That might be in California, not in New Hampshire. So I just want to say, make sure you look at your actual crop rooting depths. This is what we should be doing when we're using sensors, though. We should be graphing both or keeping records of both the shallow and the deep sensor in our soil. And reading this graph here from left to right, we start with our shallow sensor, the black line, at about 30 centibars, right? So that's, for us in New Hampshire, that would be a time to irrigate, but for this particular farm with their particular soils, it is not. They're happy with that amount of water. They're going to allow the soil to dry more. So the centibar reading goes up, 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 up on the shallow sensor till about day 11, when they say, okay, I hit 60. That's my irrigation point. And they irrigated and it drops down to about 10, like I said, right? Now, meanwhile, that deep sensor is staying plenty wet. So when they irrigated, they only had to irrigate to that shallow sensor depth, not all the way to the deep sensor depth, which could be as much as half of the water that they might have otherwise irrigated. So they would have ran that irrigation system only half of the time. So marching on from day 11, if we watch both of these sensors now, they're both drying out. And eventually that deep sensor hits 60 on day 25, and they decide to irrigate again. And of course, now they're going to irrigate to the full rooting depth of the deep sensor. It's going to be probably for twice as long, twice the volume of water to replenish that entire soil profile, that entire amount of water, available water capacity within the soil. So this is one of the ways that you can use shallow and deep sensors and this information to your advantage by only irrigating to the depth you need when you need it. And if you only have shallow plants in the ground at the moment, maybe they're young, early in the season, you just planted them, you're always just going to read that shallow sensor. That deep sensor is probably going to stay perfectly fine. Or if it gets dry, do you care? You don't have roots down there, right? So those are some of the strategies you can use. As far as equipment goes to actually read sensors, there's some variation there as well. What I'm talking about all today, they're electronic. So you could get these real simple handheld readers, and you can just run around the farm, clip the sensor, the reader to the sensor, and it's going to give you a number. Super simple, very basic. If you're a technophobe, you don't like computers, this is going to work out great for you. The problem is it's very labor intensive because you are literally running around your farm, clipping this thing onto potentially many and many sensors. You need to be very diligent about it. And ideally, when you're taking your readings, you should do it at the same time of day because, of course, soil moisture levels are going to change during the day. So if you always do it in the evening, you should always do it in the evening. Don't mess around midday, early day, late day. Be very consistent. And that just leads to people not doing this very well because it is such a manual process. It just tends not to get done as often as it should, or they're not visualizing the data in a way that helps them make decisions. So kind of moving on to the next stage of technology, it's being able to have a tool take those readings for you. So you permanently or semi-permanently attach the sensors to a logger. And that logger then is going to automatically take timely readings and store those for you so you can go and look at them later. Problem being here is these very simple loggers is you still got to go check the thing. You might be able to put several banks of sensors into it, so it can read a high and low sensor from 2 or 3 different crops, which is nice, but you got to go check it. And of course, these are a bit more money. You got to have one of these loggers every time you want to deploy it. So, and some of them are certainly not cheap. The direction, though, that the industry is going, and I'm trying to move farmers that are willing to do it, is toward smart data loggers. Smart meaning they're internet connected. So they are logging in the same way as that blue box was there out in the field. They're still doing that same thing, but instead of keeping all the data housed on the box, they're constantly feeding it into the internet, onto the cloud, so that you can access that data from your phone, from your computer, wherever you are. Very nice. And a bunch of them too, they will give you alerts when you've hit your irrigation set point. If it's 40 centibars or kilopascals, you'll get a text notification on your phone. Hey, the broccoli needs to be irrigated. Can't beat that. It's user-friendly, and a lot of these systems are designed to be farmer-friendly. That said, not all of them are. Some of them are geared more toward research or education than they are toward farmers and irrigation monitoring. So talk to your vendor, look at the products, see what's out there. I certainly have my favorites, but that's really for you to decide as a manager based on price, usability, capability, all of that. These are also not cheap. You do need to be somewhat comfortable with the technology, of course, willing to maybe troubleshoot when things don't always work right with our internet connected world these days. The other thing that rubs me the wrong way with some of them is that they have subscription fees. I'm on a bit of a personal war against subscription fees in my house right now, so that is something I'm trying to avoid as a person at the moment. For some farms, though, it absolutely may be worth the subscription for the service you get. That is up to you. The other thing is, how are they connecting to the internet? Are they cellular? Do you need to then buy a cell plan? Do you have cell service at all? Do they have a Wi-Fi option? If that's the case, do you have Wi-Fi close enough to the field? Some of them use radio waves. Some of them use mesh networks that can help to extend your Wi-Fi far beyond where it might normally reach. So lots of solutions to that technology end of it. Know though how the system you're going to use is going to operate so that it will actually work for you. All right, kind of moving on here to the last stage of the conversation is just, how can I get some help financially and technically with these systems? The NRCS specifically has some conservation programs that we've now operated for several decades. Very popular one is the Environmental Quality Incentive Program. A lot of farmers have grown to know and love this one. It funds projects at flat rate incentive through flat rate incentive payments. It's an application process. You got to meet some eligibility criteria, and it's competitive. There is ranking. I will say we've got a lot of funding for EQIP right now through the Inflation Reduction Act. Not all of that's eligible for irrigation. In fact, it generally isn't, but it means that the money's just generally going further. So if you're thinking about doing something toward improving the efficiency of your existing irrigation system, this is a great program to look at. The best thing you can do is talk to a field office and they can steer you in the right direction for a program that's going to fit your farm. I did say improving your existing system, and that is a requirement of EQIP. You had to have irrigated 2 of the last 5 years, and we have to find a way to improve the efficiency of your system. So that is a caveat of EQIP. It's the way Congress wrote the program and how they want it to operate. So that just kind of is what it is, but it's a limitation to some farmers that need a startup system. Thankfully, we do have another program for that called AMA, Agricultural Management Assistance. Very much like EQIP in all sorts. You'll notice that list of practices there is exactly the same. But the nice thing about AMA is that it's about reducing risk on your farm and using conservation as a tool for risk management. And putting in new irrigation systems is a fantastic way to mitigate your risk as a grower. So we can do startup from scratch irrigation systems that are highly efficient through AMA. The problem with AMA is we don't get nearly as much funding. In New Hampshire right now, we do have funding for this program. It tends to go fast. So again, reach out to your conservation office and start to work through that process of putting in an application and getting a plan in place. In New Hampshire specifically, we have offices all over the state. If you're visiting from another state, you're going to find the exact same thing wherever you're at across the country. Just visit your local NRCS webpage. Google's your friend there, and you can find your local office if you're not working with them already. And I'll just add too that these programs don't just do irrigation. They do everything from forestry to grazing, farmstead improvements, manure management, everything on your crop fields, cover cropping, tillage management, mulching, lots and lots of things that we can do to help you from a conservation perspective that you might not be aware of, even beyond irrigation, or to help your irrigation system function better. All right, that is all I have. I'm gonna hit the right button and stop sharing.
Awesome. Thank you so much, Chad.
Yeah,
And
fast and furious.
Great
yeah.
on time. Yeah, we have some time to spare, and we had some questions in the chat that are mostly covered, but just wanted to give folks a chance to hop in. Just before that, wanted to mention a few local funding opportunities. Chad was talking about some NRCS programs that are administered federally. So even if you're not in New Hampshire, you have access to these programs through your local field offices. We posted a link in the chat for the New Hampshire field offices, but again, yeah, Google's your friend. If you are outside of the state, you want to just Google your county plus NRCS, you'll find your local field office. But New Hampshire specific funding, we have a few options. Some of them have actually closed recently for the year, but wanted to make you aware of energy efficiency funding that's administered right here, New Hampshire. Through the conservation districts, we actually have a statewide grant program. It's the Climate Resilience Grant. It funds up to $10,000 for climate resilience projects that can include efficiency upgrades. It can include renewable energy options. And so if you're looking to explore any of the options in this efficiency series, you can get funding to make some of those upgrades. Would also like to throw out on-farm solar as an opportunity for you. Just like with the NRCS programs, these are federal programs through the Office of Rural Development, their Renewable Energy for America program. That can fund up to 50% of renewable energy projects. So if you were ever considering on-farm solar, you can get up to half of those solar projects covered. And then there's also likely statewide funding to help support the other 50%. Might not cover it all, but significantly reduces the cost of renewables. Not irrigation specific, of course, but these are systems. Your farm is an ecosystem, and everything sort of contributes to efficiency overall. If you live here in the Monadnock region, you have access to the Monadnock Food Co-op Farm Fund. That is up to $20,000 to help grow your farm business. And that can include equipment and infrastructure upgrades, looking at wholesale production. So if your farm's looking to beef your production up, you can get funding for some of these big projects, just like irrigation work, coolers, other efficiency upgrades. Really fantastic. And in the short term, we actually have an application closing in 2 days for $2,000 energy stipends. It's a really simple application process. It can cover project costs, your time to do research and legwork on efficiency projects. We'll pop that in the chat as well, but it's a really simple application process, and I don't believe we've used all those stipends yet, so highly encourage folks local to Cheshire County for now to apply to those stipends. If you're thinking about irrigation upgrades, go for it. And all of these grant funds can complement, with exception to the REAP solar program, all those grants can complement NRCS funding that Chad was talking about. So highly encourage you to think about these as a system and utilize all these opportunities available to you. If you have any questions, contact your local conservation district. I'll put a link in the chat for the New Hampshire districts. And wanted to open the floor to any questions from our audience or from some of our fellow presenters. I think Christine had a question. I'm going to pull that up. Or Christine, was your question answered by Trevor? It was about.
No, it wasn't.
Okay.
There was a statement about its reusability. I didn't hear anything about recyclable.
Great. Yeah. Chad, do you have any comments on the recyclability of that micro irrigation drip tape and what happens once it's reached its lifespan?
Yeah, Trevor actually put a comment in the chat there. Trevor Hardy at Brookdale Fruit Farm, who is an irrigation vendor that we work with quite a bit in putting designs together for farmers. We're often working directly with someone who is going to sell the product to the farmer. We verify everything is in good order and it looks like it'll work. But yeah, his comment there about recycling is probably as good as I could give. It's often tough because ag plastics are dirty. So you have to find a solution to that and specific vendors who can take ag plastics. And it looks like there is one at the moment, as long as the drip tape is wiped clean. So.
Oh, I see that. I'm sorry. It must have gone past when I was multitasking.
Yeah, no problem. Yeah, chat windows are like that. And it's going to be a regional thing a lot of times. If you're, in New Hampshire or around here, talking to your vendor like Trevor is that sells the tape is a great way to kind of get the lowdown on what is available in your area.
Thank you for that.
Definitely. Any other questions from the crowd? Awesome. Well, thank you all for being here. We'll be sending a follow-up, including today's recording. Any of the resources chatted about today, we'll include in that as well. Yeah, thank you, Chad. Your knowledge is fantastic. We really appreciate you donating your time to us today and sharing your knowledge with the masses. It's interesting hearing about, how plants might see this water source and how they actually take up water. I think that contributes a lot to efficiency, both from a water standpoint, but also an energy standpoint. If we're just running our systems constantly, we're not doing a good job, as good of a job as we think we might be. So getting it right seems to be the key.
And I'll just say too that these systems scale up and down very, very easily. So if you're small scale, micro irrigation is just as good as fit for you, oftentimes as it is for large scale growers. Very similar technology and solutions are available on a small scale. The same thing goes with soil moisture monitoring. And the NRCS programs have a lot of now small scale scenarios for being able to provide higher cost share or incentive rates to small farms, where in the past, if you tried to work with us, potentially you found out we weren't paying very much because we pay by acre, where you're in the square foot kind of zone. We've gotten a lot better with that. So even if you're a small farmer and these things sound good, yeah, give us a ring.
Thank you so much. Yeah, and Trevor just posted in the chat that there's an additional meeting on irrigation Saturday the 17th. So that's coming up this Saturday. Looks like it's an all-day meeting in Massachusetts in Shirley, Mass. We actually have a couple more workshops coming up. We have an on-farm solar webinar next week, same time, Tuesday, 12:30 to 1:30. That'll be taught by Chris Lent from the National Center for Appropriate Technology. If you wanted to explore solar for your farm, that's a great space to do it. We have an in-person workshop on the Renewable Energy for America program. There's representatives in New Hampshire who can help you write your grant, so that 50% off renewables, you can receive support. So that's for farmers. We have a maple producers on-farm tour here in Westmoreland, New Hampshire at Stewart & John's. That'll be March 12th. And we have a high tunnel efficiency program on March 26th. That'll be in person. We're touring a new high tunnel put up by Dog Days Farm in Fitzwilliam. I believe we only have one spot left for that workshop, and if you want to be the last one there, we'll follow the link that says Energy Efficiency Series, and you can nab that last spot. Thank you all for being here. Teresa, any final words?
Just that if anybody's interested in learning more about organic production or transitioning, give me a call on Thursday in the evening, third Thursday of every month at 6:30. I host the Farmers Organic Roundtable. You can come and talk to other farmers and network. You don't have to be organic to come. Just come and talk with farmers.
Love that. And Teresa's
Yeah.
a farmer herself, so
I
you'll be in
am.
good company. Chad, any parting wisdom?
No, I think I'm all set, Matt. Thanks, everyone.
Awesome. Yeah, thank you all. Have a wonderful rest of your week. Take care.
You as well.
Bye, everyone.